Okay, this is the core assessment 3. These are our questions. Let's dive in. I'm going to go through each of them as I would answer them, so you can check your work a little bit better and see exactly where you went wrong. So, question 1. Bit blurry, I'll make it bigger. Jessica, a maths student, is asked by her teacher. You can read the question. She's done some working out here and she's done something wrong. We need to say, well, what has she done wrong? Best way to answer these questions is to just do it yourself, and see what disagrees in your working out. So I'm going to go ahead and do this. So I'm going to solve tan x equals to sine x. I'm going to switch tan to be sine x over cos x. That equals sine x. I'm going to times by cos x, so sine x equals to sine cos, and then I'm going to subtract it to get it over here. So sine x subtract sine cos equals to 0. Kind of I'm on the right step where she is here, but she's cancelled out sine. Never ever do that. You can't just cancel out by a variable something you're wanting to find. So if you had something that was like this, you'd never just cancel out sine and say this. You would have always factorized it out, because that gives you a solution of x equals 0 and x equals 1. If you just cancelled it and said that, your only solution would be x equals to 1. But x equals 0 is also a solution. So when you cancel out a variable like that, you would know in this case here that that is wrong. It's the same thing with sine. So I need to factorize out sine. So I've got the case for this to be true. Sine x equals 0, or 1 minus cos x equals 0, so cos x equals 1. From there, well, I would get solutions of this to be 0 and 180 degrees, and I would get the solution of this to be 0 or 360 degrees. So my solutions would be 0, 180 and 360. We can see she's missed out the 180 because she'll have just got these two solutions here and she wouldn't have got these two. This one being overlapped, but she'll have missed the 180. So what has she done wrong? Well, she shouldn't have cancelled out the sine. So let's read exactly what we're kind of having to write. This teacher tells Jessica that she has not found all the solutions for goodness sake. Can't cancel out sine x, as you will lose potential solutions, as we've very clearly shown there. Question 2. So binomial expansion, I've got what you would get in your formula book there, so you were fine to use that. So it's not something you need to know off the top of your head, but you need to know how to use it. Let's find the first 3 terms. So within this, well, a is going to be 1, b is going to be minus 2x, and n is going to be 10. So first 3 terms, we're going to be using the an plus this n1 in kind of the vector brackets. That's the same as saying n choose 1. And you can do that in your calculator. You would type 10 choose r, 10 cr. And then we would carry it on with this, and this would be n choose 2. So we're kind of lowering the power of a each time, and we're highering the power of b each time. B doesn't appear here because it's b to the power of 0. That would just be 1. So 1 to the power of 10 plus 10 choose 1 to the power of 9 times by negative 2x plus 10 choose 2 1 to the power of 8 minus 2x all squared. So this is just 1. My 10 choose 1 is 10, 1 to the power of 9 is 9, and this goes here. 10 choose 2 is 45. 1 to the power of 8 is just 1. And minus 2x all squared is 4x, positive 4x squared. So then we've got 1 subtract 20x plus 180 x squared. That is our first 3 terms. And if you ever wonder why we never seem to go more than 3 or 4 terms, get yourself on a graph plotting tool like GeoGebra, plot the first one, so just plot the graph 1, then plot with 2 terms, then plot with 3 terms, plot it with 4 terms, plot it with 5 terms, and see how once we kind of get past the 4th term, it doesn't make the graph much more accurate to if you plotted the actual, if you actually plotted the actual thing, the exact one. And you'll see why we generally just seem to stop after 3 terms, because it just doesn't seem to give us much more accuracy. I'm going to start part B off here, then I'm going to scroll down. So, she wants to evaluate 0.998 to the power of 10. And she's going to use a value of x that's going to make this become the same. So what value of x is going to make this true? Well, the value of x would be 0.001. So I want to substitute in we want to sub in x equals to 0.001 into our thing we just found here. So 1 subtract 20 lots of 0.001 plus 180 0.001 all squared. And when we do that, we're going to get 0.98018. And to 5 decimal places, yeah, we've got no, show that it's correct to 5 decimal places. Well, we want to stick this in, then we want to stick it into what 0.998 to the power of 10 would actually be equal to. When I chuck that into my calculator, that's going to be 0.980179, so to 5 decimal places. Yep, exactly the same to 5 decimal places, so we've shown that they are the same. Okay, question 3. Differentiating from first principles. So this is what you'll have got in your formula book. We just need to know how to use it. So, first of all, you probably know what you're expecting to get at the end. You're expecting to get 6x plus 4 because we can differentiate with our other method of doing it. But through first principles. So, f dash x equals the limit as h goes to 0 of f brackets x plus h over h. We'll get really bored of writing the limit to h equals to 0 over this question, but we've got to keep doing it. So, f of x is 3x squared plus 4x. So for this f of x plus h, we just need to put x plus h instead of x in these two things. So I'm going to get 3 brackets x plus h squared plus 4 brackets x plus h. And then I'm going to subtract all of this because that's just f of x there. and that's going to be over h. So keep going down, always remember to write that. We're going to expand these brackets. 3 brackets x squared plus 2xh plus h squared plus 4x plus 4h minus 3x squared minus 4x all over h. Give ourselves a bit more room. Limit as h goes to 0. Let's expand this bracket now. So 3x squared plus 6xh plus 3h squared plus 4x plus 4h minus 3x squared minus 4x all over h. Let's cancel some stuff out. We've got a minus 3x squared and a positive 3x squared. We've got a minus 4x and a positive 4x. So going down, let's see what we've got left. 6xh plus 3h squared plus 4h. Our x's should pretty much all cancel. Anything that isn't connected to a h should really disappear, and we know we're doing it. We're on the right lines. So we can divide through by h now. There's a h in each term, so let's get rid of that. So we've got 6x plus 3h plus 4. Very important step here. We need to say, well, as h goes to 0, because this is what this whole limit thing here means, as h gets really small, what happens to our things? Well, 6x isn't going to change, 4 isn't going to change, but 3h is also going to tend to 0, because 3 times something going towards 0 is 0. So at that stage we can get rid of our limit, because we've applied the limit now. And that's just going to leave us with 6x plus 4. So we've done. So we've differentiated it by first principles, and we've got exactly what we were expecting to get, seeing as we already know how to differentiate normally. So there we go. One more scroll down. That's the final answer. Okay. This is a bit of a long question, 7 marker. But it's not too bad. It's not too bad. So, formatting on this went a little bit off. That plus 3 should be there, so we can ignore that. So, Chris claims for any given value of x, the gradient of this curve is always greater than the gradient of this curve. Show why Chris is wrong by finding all the values of x for which his claim is not true. So, first of all, I'm going to call this 1 and 2. So let's deal with number 1 first. Let's find the gradient function, and we know that's by differentiating. So the gradient function of this would be 6x squared plus 12x minus 12. And let's do number 2. The 1 would disappear, so we'd get 6d subtract 12x. Chris's statement, so what Chris is saying, he says that this number 1 is always greater than number 2. So in terms of what we've just found, he's saying this. But we're trying to prove that he's wrong. So the opposite of his statement, so show that Chris is wrong by finding all the values of x. His claim's not true, so if Chris is false, we flip the statement. Well, it's either going to be less than or equal to. That's the opposite of it being greater than, less than or equal to. So we're going to work with this, and we're going to find values where for this inequality being true, and that'll be the values where Chris is wrong. So we want to get it towards 0, we want to factorize it, draw a little graph and see which part of the graph we're going to get our inequalities from. So let's go ahead and do that. So 6x squared plus 24x minus 72 is less than or equal to 0. I can divide through by 6. We're fine to divide through by numbers, just not by variables. If you're thinking back to question 1 and you think I'm contradicting what I said then, I am not. I'm just dividing through by a constant, which is completely fine. And I factorise it. So x is minus 6, x is 2. I'm going to plot a quick sketch of this graph here. So we've got minus 6 and we've got 2. It's a positive graph. So it's going to go like this, and we want to check where it is less than or equal to 0. So that is going to be the stuff down here. Less than 0 on our y's. So the inequality for that is this. So you can always double check. You can find some numbers in between here, plug them into our differentiated things and see where it goes. You can get on a graphing tool and you can plot this and you can plot this, and you'd visually be able to see that this is true between these values, but it's not true between the other values. So you can do a bit of exploring for yourself around that and see if you can get a really good understanding behind. We've done a lot of abstract maths. Sometimes it's good to see the graphs. I know Mr. Hart and Mr. Joy even have some pink t-shirts printed saying sketch the graph. So okie dokie. Question 5. This is going to be a bit of a long one. I may take a break halfway through. So first of all, I'm going to change this to be a form we like. So hopefully I've not done anything crazy here and you've followed through. If not, maybe you want to go back in the textbook and check your indices work. So let's find dy by dx. So this is question A. It's easy once we get it to this stage. So what we need to do is times by the power, take 1 off the power. Oops, that's not going to be a positive. I always do that. Times by the power, take 1 off the power. Don't put it to 0 because you think 1 take away 1 is 0. Remember, it's a minus 1. Thinking number lines. Anyway, that's that. Part B, we want to find the coordinates where the tangent to the curve crosses the x-axis. So there's a lot of stuff to do here. First, we want to find the equation of the tangent first. So I'm going to go ahead and do that. I've been given an x-coordinate. I'm going to find the y-coordinate. So at x equals 4, y equals 2, I'm going to use this. Probably most likely I'm going to use that because I can chuck it all in my calculator. So I will put out what I'm typing in my calculator. So, oopsies. Meant to be substituting in 4, aren't I? So, when I launch that into my calculator, when I've done at home, what did I get? I got 56. So the coordinate, which there's a coordinate that lies on our curve. It has this, and that is point A. So that's also going to be a coordinate. It's going to be on the curve, and it's also going to be on the tangent because we're finding the tangent at A. So next of all, let's find the gradient of the tangent at x equals 4, and we're going to do that by plugging 4 into our differentiated function. So again, just be really careful about your brackets. Let's chuck this in the calculator, or you can go through it step by step in your head if you don't trust your calculator like I don't do. Our gradient is 16, so we've got a gradient and a point. We can say y equals to 16x plus c, and then we know the coordinate is 456, so 56 equals to 16. Here we go. 56 equals to 64 plus c, c equals to minus 8. So therefore the equation of our tangent is this. You can also do the formula you've got for finding it with a point. What is it? Y minus y1 equals to m brackets x minus x1. If you like that, you can also use this. If you don't like doing it the way I've done, I prefer doing it my way, but that's me, obviously. So, final bit, we want to find the coordinate where it touches the x-axis. So, x-axis is at y equals to 0. So 0 equals to 16x minus 8. 16x equals 8. X equals 0.5. So it touches the x-axis at 0.5, 0. That is the final answer. That is your coordinate. Bit of a long question there. This question was, I thought, was the hardest one. Just because I went down the wrong route and I tried to organise and rearrange it to make it an equation with sine. It took me my second go to realise I had to make an equation with tan. This always gives me a little hint where it says where cos doesn't equal 0. That's basically saying, well, they want me to divide by cos at some stage because they don't want me to have a 0 on the bottom of a fraction. Anyway, we have to use some of our trig identities here to make them either all coses, all sine, or all tan. What I'm going to do to start with is I'm going to divide by cos. This can, I don't know, this really can just be a bit of a, just try something until it works. Try and make it into sines. If that doesn't work, try and make it into coses. If that doesn't work, try and make it into tans. You've only got 2 or 3 things we can use at this stage, so if you hit a brick wall, it's probably because it is a brick wall. So just start again, rub it all out, try again. So I'm going to divide by cos. Sine over cos. Tan plus 2 sine over cos equals 3. Remember, things we know at this stage is this, and rearrangements of them. So that's what we're kind of using. They're the 2 things we know. So I can say, well, this is going to be tan, and because it's tan, I can say that's tan squared, it's tan by tan. This is 2 tan, and I'm going to subtract a 3 over to the other side as well at the same time, just to save me a line of working. Time to factorise. If you want to, just imagine this is x, so you could just think of it as x squared plus 2x minus 3, and you should know that that is x plus 3, x minus 1 equals 0, so if we go back to the actual working, it's going to be tan theta plus 3 and tan theta minus 1. So we know that tan theta equals minus 3 or tan theta equals to 1. We're going to jump in our calculator and we're going to do some inverse tan. So if I take us up to here now to carry on our working. So we get, if we do inverse tan of negative 3, we are going to get, so tan inverse of negative 3, we're going to get minus 71.565. And if we do tan minus 1 of 1, we are going to get 45. We're trying to find values between 0 and 180. So this obviously isn't going to fly. This works. We don't just leave it there though. We know that sine, cos and tan are cyclical. They repeat patterns all the time. So give yourself a quick sketch of tan. between the values you're wanting. So I know that's 90, and I know that this here is 180, and here is 0. So I'm going for stuff between here. Any values between there. I'm going to label on 45. So I've got 45 probably somewhere like here. This can be 45. If I go across, I get one solution there. I don't get any more solutions before I hit my deadline. If I carried on for a bit, I would have another solution here, but I don't. So that just stays as one solution from here. If I label on my minus 71, well, I know that this is going to be minus 90, so it's just going to be somewhere here. Doesn't really matter how accurate you are. But I'm going to say minus 71 somewhere like this. And if I continue that line across, here we go. This is how far I want to go between my kind of red hooked bit. I've got no solution in this section. I have one solution there. It's not minus 71, but I know I can use this to find another solution. If this is 71 away from 0, where I hit this part, the x-axis, I know it's also going to be negative 71.565 away from the 180, where it also hits the x-axis. So I know it's going to be 71.565 away from 180. So I can get a solution by doing 180 take away 71.565, and that's going to get me 108.43. I'm going to keep it as 108.4 degrees. So my two solutions are these two. So I've used this to get me to here, and this one only gave me that solution, but I felt like it was worth still checking that no other solutions fell between in my diagram. You might do this through a cast diagram. I like doing it through the actual drawings of the graphs, but if you've done it correct through a cast diagram, then I'm not going to stop you. Okay, where's my final two? I think I've dropped down for these. Okay, some more solving. So maybe I'll do part A on this screen and I'll copy and paste to get part B fit on. So, solving for sine squared x plus 8 cos x minus 7 equals 0, and we're doing it between these values. So, remember we said this, so we can actually say, well, sine squared equals to 1 subtract cos squared. So I'm going to use that for lots of that. And then I'm going to expand this bracket. 4 minus 4 cos squared plus 8 cos. Oh, I'm mixing between, you know what, I'm going to do it all as thetas because I like drawing thetas better than x's. I'm changing it all to thetas. Then I'm going to rearrange it to get me a positive amount of cos squared, because it's just a lot easier to factorise from there. So taking everything to the other side, that'll be positive 7, then it'll make it positive 3. When I go to factorise this, I'm going to have, I think it's 2 cos in both of the brackets. 2 cos, subtract 3, 2 cos, subtract 1, equals to 0. So then I've got cos equals to 3 over 2, and cos equals to 1/2. This is actually invalid. If you try and inverse that, it's not going to work. Cos goes between 1 and -1, so we don't get any solution from this. However, we get a solution of 60 for this. However, don't just stop there. We've got to check between 0 and 360. So draw yourself a rough cos graph that goes between 0 and 360. So 360, 270, 180, 90, 1. That'll be 0. And this is -1. Okay, so 60 in a different colour is going to be somewhere roughly like this. Where does that get me a solution? Here. That's a half. So I need you to continue that all the way. I'm going to have two solutions here. So if that is 60 from here, then it's also going to be 60 from this one. So, because if we continued this down, we're symmetrical around the y-axis. So 60 this way is also the same as 60 that way. So we're going to have a difference of 60 here. So we're also going to have 300 degrees. So our final answers are 60 and 300 degrees. And part B, I'll rewrite out the question again, and I shall do it in a different colour. B. So if we did this, if it was changed for this, what would happen to the answers? Well, we've got half of this in here, so we'd need, we're half in it, so we'd need double the value of theta for this to be true. So instead of it being 60 and 300, it would actually be 120 and 600. Because if we put 600 here, it would be 600 divided by 2 gives us 300, and we know that works. 120 divided by 2 gives us 60, and we've proved that that works in the last question. However, that's too large. So our value is just 120 degrees that works. Everything else is not in the range we're wanting. And then have we got one more question? So, a bit of ambiguous case sine or cosine rule. So we've got a triangle ABC. AB is 12 centimetres. And CAB, so A, B, C is going to be somewhere down there. We've got a degree of 40. So in red, this is either going to be 8 centimetres. Well, I mean, it could be like that. And it also could be like that. So C could be either of these. But we know that these lines are 8 centimetres. And we're wanting to find this angle or this angle. Just to help me visualise it a little bit better, I'm just going to draw one of the cases. The calculator and my brain will do the rest of the working out. This will just help me visualise whether I want to do sine or cosine. Okay, so from here I'm going to whip out my fancy colour for the final question, as I always do. Look at this. Beautiful. We've got some pairs. So we're going to be doing sine rule. So sine of theta over 12 equals to sine of 40 over 8. So sine theta equals to 12 sine 40 over 8. So 12 sine 40 over 8 equals to 0.96, 418, etc. And then if we do the inverse of that, so inverse sine of the answer, that's going to be 74.61, 856, etc. Obviously we can tell my diagram is not right. That would actually be this angle. That would actually be that angle there. We can just tell by it looking acute. I'm going to draw this diagram out a little bit bigger, because the way I'm going to explain this, it's going to help if it's drawn bigger. So we know that is that. These lines are both going to be 8 centimeters, so it's actually an isosceles triangle. So this angle is the same as that. That's also 74.61. So this angle is 180, take away 74.61. You can also look at it through your sine graph, but if you can just use some basic angle rules, why not? So this angle here is going to be 105.38, and I'm going to call that 105, so or my other fancy colour equals to 105.4, and we can probably call that just 0.6. So there are our two answers to this question. Okay, I hope that wasn't too boring for you.